بسم الله الرحمن الرحيم. بنرحب فيكم في محاضرة رقم 19 في الإجراءات الإشارية الرقمية. اليوم رح نتكلم عن the properties of the Z transform. Properties of the Z transform. Okay. The first property is linearity, and this is applicable because of the definition of the Z transform itself. Now, if you have x1 of n that has Z transform of x1 of z, and x2 of n that has Z transform x2 of z, and this one has ROC1 and this one has ROC2, let's say. So we can say that alpha x1 of n plus beta x2 of n has the Z transform of alpha x1 of z plus beta x2 of z, with the ROC equals to ROC1 intersection ROC2, the intersection of the overlap between the two regions of convergence. Okay, so this is the linearity. Based on this, I'm gonna find part of the table that we have for the Z transform, which we are going to use for doing the inverse of the Z transform by inspection. The examples here are two examples. X of n equals, let's say that this is part A, x of n equals to cosine omega 0 n mu of n, and the second one is x of n equals to sine omega 0 n mu of n. Okay, I'm gonna do the first one, and I'm gonna let the second one as an exercise for you to do it by yourself. So let's do the first one. Find, what is required here is we need to find x of z for both cases. Okay, all right. So for part A, we have x of n equals to cosine omega 0 n mu of n, and this can be written as, using the Euler formula in the complex, as 1/2 e to the j omega 0 n plus e to the minus j 0 n times mu of n. And this is equals to 1/2 e to the j 0 n mu of n plus 1/2 e to the minus j omega 0 n mu of n. Okay. So the first, I'm going to take e to the j omega 0 n mu of n as x1. What is the Z transform of this one? This is equals to 1/1 minus e to the j omega z inverse. This is our alpha to the n j omega 0. And ROC is magnitude of z is greater than 1, because e to the j omega 0 magnitude is equal to 1. Also, e to the minus j omega 0 n mu of n has the Z transform 1/1 minus e to the minus j omega 0 z inverse, and the ROC also magnitude of z is greater than 1, because the magnitude of this one and this one are the same. It's equal to 1. Okay, so x of z is 1/2 the transformation of this one plus 1/2 the transformation of this one. So x of z is equal to, by linearity, so alpha here is 1/2 and beta here is also 1/2. So this is 1/2 times 1 over 1 minus e to the j omega 0 z inverse plus another half 1 over 1 minus j omega 0 z inverse, and the ROC is the combination or the overlap, which is magnitude of z is also greater than 1, because both have the same region. Okay, I'm gonna do this as a summation. You have 1/2 outside from both of them. Now I'm gonna combine those, so 1 minus e to the j omega 0, z inverse times 1 minus e to the minus j omega 0 z inverse. And here we have 1 minus e to the minus j omega 0 z inverse plus 1 minus e to the j omega 0 z inverse. If you multiply, combine those two, so you have here, as I'm using the Euler formula for complex quantities, we can have x of z equals to 1/2, and here in the numerator you have 2 minus 2 z inverse cosine omega 0 over 1 minus 2 z inverse cosine omega 0 plus z to the minus 2. So 1/2 will go with those two, and the final answer for x of z is equal to 1 minus z inverse cosine omega 0 over 1 minus 2 z inverse cosine omega 0 plus z to the minus 2, and our ROC magnitude of z is greater than 1. Okay? If you do part B with the same procedure, then we can find that sine omega 0 n mu of n has the z transform equals to z inverse sine omega 0 over the same denominator, 1 minus 2 z inverse cosine omega 0 plus z to the minus 2, and here also the ROC magnitude of z is greater than 1. Okay, do the same procedure as we did here. You have the sine expanded as the cosine 1 over 2j e to the j omega 0 minus e to the minus j omega 0 n. Do this and you will end up with the same, with this result here. Okay, so this is for linearity. The second property or the second theorem is time shifting. So time shifting, if you have x of n that has the z transform as x of z, then x of n minus k has the z transform to be z to the minus k x of z. Okay? And we actually did this before when we did the time advance and time delay. So if k is positive, you have time delay. If k is negative, you have a time advance. Okay? Let's do an example. We have x of n equals to 1 to 5. So we take a finite sequence, 7, 0, and 1. And you have the 0 here, the default 0. And x of z for this sequence is equal to 1 plus 2 z inverse plus 5 z to the minus 2 plus 7 z to the minus 3 plus 0 z to the minus 4 plus 1 times z to the minus 5. Okay, so this is our x of z. And here the ROC, you have a finite sequence. It is the entire z-plane except z equals 0. Why 0? Because this is z inverse. It's 1 over z, 1 over z squared, 1 over z cubed, and 1 over z to the power 5. When z equals 0, then x of z is infinity and it diverges. Okay, now if x1 of n is equal to x of n plus 2 and x2 of n equals x of n minus 2, find x1 of z and x2 of z. So x1 of z is equal to x1 of z, you have k equals minus minus, so k equals minus 2. So you will have z to the power 2, yeah, because this is minus k and k is plus 2, sorry, minus 2. So you have minus minus x of plus 2, and you have k, then your k is equal minus 2, z to the minus minus 2, so it's z squared, and this is the time advance as it's shown here. So you multiply it by z to the power 2, positive power of z, times x of z. So this is equals to z squared times 1 plus 2z inverse plus 5z minus 2 plus 7z to the minus 3 plus z to the minus 5, and this is equals to z squared plus 2z plus 5 plus 7z inverse plus z to the minus 3. So you can see that now the ROC of this sequence, the ROC of this x1 of z is the entire z-plane except z equals 0 for those two and z equals infinity for those two. So the z equals 0 for the negative power and z equals infinity for the positive power. So z cannot be infinity because of those two, and z cannot be 0 because of those two negative powers. Okay? Let's go let's see the second one. Now, for the second one, k is equals to k equals here positive 2. So x2 of z is equal to z to the minus 2 x of z is equal z to the minus 2 times 1 plus 2z minus 1 plus 5z minus 2 plus 7z minus 3 plus z to the minus 5. And this will go deeper in delay. So this is z to the minus 2 plus 2z to the minus 3 plus 5z to the minus 4 plus 7z to the minus 5 plus z to the minus 7. And here the ROC still the entire z-plane except z equals 0. All those are negative powers, so we don't have infinity here within the region, the exception of the region of convergence. Okay, so this is how we do shifting. You can do shifting also in time if you want, and do the Z transform also. It works in the time domain. Okay, third one is scaling. Scaling in the Z domain. Scaling in the Z domain, if you have x of n that has the Z transform as x of z with the ROC is equal to the magnitude of z is greater than R1 less than R2, then if you have a sequence as a to the n x of n, then the Z transform of this is equal to x of A inverse z, which is equal also to x of z over A. And the ROC now is the magnitude of A times R1 less than the magnitude of z less than the magnitude of A times R2. So this is for any constant A real, whether it is real or complex. So whether it is a real or a complex constant, it works with no problems. Okay. I'm gonna go back to the examples before and see what will happen if we have a damped sinusoids sequences. So the example here that we are going to look for are the determine the Z transform of the signals A, x of n equals A to the n cosine omega 0 n mu of n, and B, x of n is equal to A to the n sine omega 0 n mu of n. We did this example before without having A to the n with it. So it was pure sinusoid. Now it's damped sinusoid or exponentially sinusoid sequences. So just to remind you, previously we had cosine omega 0 n mu of n. It has the Z transform, which is equal to 1 minus Z inverse cosine omega 0 over 1 minus 2 Z inverse cosine omega 0 plus Z to the minus 2. Okay? Now we have A to the n cosine, so this sequence has this transformation, and we will look at the scaling in the Z domain. Now if you have A to the n x of n, this is equals to x of z over A. So we are going to substitute for each z as z over A. So A to the n cosine omega 0 n mu of n should have the Z transform, which is equal to 1 minus, instead of Z, I'm going to substitute Z over A to the minus 1 cosine omega 0 divided by 1 minus 2 Z over A inverse cosine omega 0 plus Z over A to the minus 2. Okay, just, with a little bit of manipulations, you can see that this is equals 1 minus A Z inverse cosine omega 0 over 1 minus 2A Z inverse cosine omega 0 plus A squared Z to the minus 2. And the region of convergence here, magnitude of Z is greater than the magnitude of A. Because the magnitude of the region of convergence here for this case was magnitude of Z is greater than 1. So it will be scaled by the magnitude of A. Magnitude of Z is greater than 1. So magnitude of Z will be greater than A. Doing the same thing for the second part, we can conclude that the an sine omega 0 n mu of n, it should have the Z transform, which is equal to A Z inverse sine omega 0 divided by 1 minus 2A Z inverse cosine omega 0 plus A squared Z to the minus 2. The same denominator. The numerator here has cosine and here has the sine. Okay, with the same, our region of convergence is also magnitude of greater than magnitude of A. Okay, so this is the second one, and those two are actually part of the table that we will use for inspection for the inverse of the Z transform. Okay, property number 4 is time reversal. So we have x of n has the Z transform equals to x of z, and the ROC, as we mentioned, magnitude of z is greater than R1, less than R2. If we have x of minus n, this has the Z transform of x of z inverse, and the ROC has the 1 over R2 less than magnitude of z less than 1 over R1. If we have, as an example, we want to determine the Z transform of the signal mu of n, the signal x of n equals to mu of minus n. Okay, so this is the sequence that has ones from n equals 0, minus 1, so this is mu of minus n, ones from 0 going back to minus infinity. So here we have mu of n, it has the Z transform of 1 over 1 minus Z inverse, and magnitude of Z is greater than 1. mu of minus n has the z transform as 1 over 1 minus z, and magnitude of z is less than 1. So you have, this is a left-sided sequence, this is a right-sided sequence, and this is the z transform based on the time reversal property. Okay. Property number 5. Differentiation in the z domain. Differentiation in the z domain, if you have x of n that has the z transform of x of z, then x of n has the z transform as minus z dx of z by dz. Okay? This can be proven by differentiation of the definition itself and look at the time domain sequence, and you can find the answer. Okay, we'll take an example here, which is also part of the table. If you have x of n is equal to n a to the n mu of n. So this is a sequence. Let's assume that we need to find x of z for this sequence. Now I'm gonna let x of z equals n x1 of n, where x1 of n is equal to a to the n mu of n. Okay? So if this is the case, and we know that x1 of z is equal to 1 over 1 minus a z inverse, and the magnitude of z is greater than the magnitude of a. This is x1 of z. Now I'm going to differentiate dx1 of z by dz. So this is equals to 1 minus a z inverse squared, and then you have to differentiate with a minus sign, so this is minus a z to the minus 2. Okay? So this is the differentiation of this one with respect to z. Now I'm gonna multiply this by minus z, multiply this also by minus z. So if we multiply this, then you end up with a z inverse over 1 minus a z inverse squared. This is the the answer for nx of n for the differentiation of this one. Okay. Of course, the magnitude of z is also greater than the magnitude of a. The same region of convergence as the sequence itself. One special case of this, if we set a equals 1, then n mu of n has the z transform to be z inverse over 1 minus z inverse squared, and magnitude of z is greater than 1. Okay. All right. So this is differentiation in the Z domain. Okay, the sixth property is a very important property here, which is the convolution of two sequences. If you have x1 of n with the Z transform x1 of Z, and x2 of n with the Z transform x2 of Z, then the convolution sum x1 of n convolve star circle x2 of n. So this is the convolution sum of those two, has the Z transform as the multiplication in the Z domain, x1 of Z times x2 of Z. And the region of convergence is the ROC1 intersection ROC2. Okay? Let's take an example which we had before. The example here is two sequences. The first one, x1 of n is equal to 1, 2, 0, and 1, and x2 of n is equal to 2, 2, 1, and 1. And we would like to do the convolution, but using the Z transform and Z transform inverse. So use the Z transform to perform the convolution of the two sequences. Okay, so x1 of Z is equal to 1 plus 2 Z inverse plus 0 Z to the minus 2 plus Z to the minus 3. This is the Z transform. I actually put the 0 here, which supposedly we have to take it out, but I put it here because I'm gonna do it, the multiplication with the orders of the polynomials, so I'm gonna make use of it. x2 of Z is equal to 2 plus 2Z inverse plus Z to the minus 2 plus Z to the minus 3. So this is those two polynomials. We are going to multiply those two polynomials, and we will have x1 of Z times x2 of Z. So we are going to take the first element, multiply it by the whole, all the elements of x1 of Z. So 2 times 1, 2 plus 4 Z inverse plus 0 Z to the minus 2 plus 2 Z to the minus 3. So we have the first one. Now the second element here, I'm going to multiply it by the whole polynomial up. Z inverse times this one, so this is plus Z inverse x2 of Z, sorry, this is 2Z inverse. Yeah, it's 2, 1, 1. Yeah, I'm sorry about this. This is 2. Yeah, 2Z inverse plus 4 Z to the minus 2 plus 0 Z to the minus 3 plus 2 Z to the minus 4. Okay, now I'm going to take the third element, minus 2, so 2Z plus 1 times Z to the minus 2 plus 2Z to the minus 3 plus 0 Z to the minus 4 plus Z to the minus 5. And the last one is this element here also, Z to the minus 3 times 1, it's plus 1 times Z to the minus 3 plus 2 Z to the minus 4 plus 0 z to the minus 5 plus z to the minus 6. No more. So the polynomials here, they keep the locations, or they reserve the locations of the coefficients. So we add here 2 as a constant plus 6 z to the minus 1 plus 5 z to the minus 2 plus another 5 z to the minus 3 plus 4 z to the minus 4 plus z to the minus 5 plus z to the minus 6. So this is the z transform of the convolution of those two. We can go backward to find the sequence by inspection, going to the definition and knowing that this coefficient has an order for n equals 1. This is for n equals 0. This coefficient for n equals 1, 2, 3, 4, 5, and 6. So we can say that our x of n is equal to the z inverse of x of z, and this is equals to 2, 6, 5, 5, 4, 1, and 1. And our 0 is here. And I think this is actually the same as the one that we had before. Okay? But this one, we do it with the z transform, that we perform the convolution using the z transform and the z transform inverse. Okay. Property number 7, and this is the last property. This is the initial value theorem. The initial value theorem. If x of n is causal, i.e. x of n equals 0 for n less than 0, then x of 0 in time domain equals to the limit for x of z as z approaches infinity. Okay? What does that mean? It means that, first of all, there is a condition for the initial value theorem, which means that x of n should be a causal sequence. So it starts from n equals 0 and above. Okay? And if we want to prove this, since x of n is causal, so x of z, which is equal by definition from n equals 0 up to infinity, because it is causal, so it starts from 0 and above. So we have x of n z to the minus n, and this is equals to x at 0 plus x of 1 z inverse, x of 2 is 2, and goes to infinity. Now if we take the limit of x of z as z goes to infinity, all those are negative power of z, so at infinity they all go to 0. So this one will be 0, this one will be 0, and all of them is equal to 0. So you have x of 0. This is the only constant that does not vanish in those terms. So this is one thing that we can make use of, which is called the initial value theorem. With this, we conclude our discussion about the properties and theorems regarding the Z transform. I would like to thank you, and I hope that you will find this lecture interesting. See you in next lecture.